Vibrations and waves. Describe the period of a pendulum. Describe the characteristics and properties of waves. Describe wave motion. Describe how to calculate the speed of a wave. Give examples of transverse waves. Give an example of a longitudinal wave. Explain what causes interference patterns. Describe how a standing wave occurs. Describe how the apparent frequency of waves change as a wave source moves. Describe bow waves. Describe sonic booms. The big idea. Waves transmit energy through space and time. All around us we see things that wiggle and jiggle. Even things too small to see, such as atoms, are constantly wiggling and jiggling. A repeating back and forth motion about an equilibrium position is a vibration. A vibration cannot exist in one instant. It needs time to move back and forth. Strike a bell and the vibrations will continue for some time before they die down. A disturbance that is transmitted progressively from one place to the next with no actual transport of matter is a wave. A wave cannot exist in one place, but must extend from one place to another. Light and sound are both forms of energy that move through space as waves. This chapter is about vibrations and waves, and the following chapters continue with the study of sound and light. What are standing waves? Fill a foam cup nearly to the top with water. Place the cup on a smooth, dry surface. While applying a moderate downward pressure, drag the cup across the surface. Adjust the downward pressure on the cup until a pattern of waves, called standing waves, appears on the surface of the water. Now try to change the pattern by altering both the speed of the cup and the downward pressure. Observing. Describe the pattern that you produced on the surface of the water. Predicting. What do you think might happen if you were to drag the cup on a different kind of surface? Making generalizations. Do you think standing waves can be produced in other media? Explain. 25.1. Vibrations of a pendulum. Suspend a stone at the end of a string and you have a simple pendulum. Pendulums like the one in figure 25.1 swing back and forth with such regularity that they have long been used to control the motion of clocks. Galileo discovered that the time a pendulum takes to swing back and forth through small angles depends on the length of the pendulum. The mass has no effect. The time of a back and forth swing of the pendulum is called the period. The period of the pendulum depends only on the length of the pendulum and the acceleration of gravity. 25.1. Two pendulums of the same length have the same period regardless of mass. A long pendulum has a longer period than a shorter pendulum. That is, it swings back and forth more slowly, less frequently than a short pendulum. When walking, we allow our legs to swing with the help of gravity, like a pendulum. In the same way that a long pendulum has a greater period, a person with long legs tends to move with a slower stride than a person with short legs. This is most noticeable in long-legged animals such as giraffes and horses, which run with a slower gait than do short-legged animals such as hamsters and mice. Concept check. What determines the period of a pendulum? 25.2. Wave description. The back and forth vibratory motion, often called oscillatory motion, of a swinging pendulum is called simple harmonic motion. The pendulum bob filled with sand in figure 25.2 exhibits simple harmonic motion above a conveyor belt. When the conveyor belt is stationary, the sand traces out a straight line. More interestingly, when the conveyor belt is moving at constant speed, the sand traces out a special curve known as a sine curve. Notes: be clear about the distinction between frequency and speed. How frequently a wave vibrates is altogether different from how fast it moves from one location to another. Figure 25.2. Frank Oppenheimer, founder of the Exploratorium Science Museum in San Francisco, demonstrates that a pendulum swinging back and forth traces out a straight line over a stationary surface and a sine wave curve when the surface moves at constant speed. Think, what is the frequency and vibration per second of a 100 hertz wave? A 100 hertz wave vibrates 100 times per second. A sine curve is a pictorial representation of a wave. A source of all waves is something that vibrates. The parts of a wave. A weight attached to a spring undergoes vertical simple harmonic motion, as in figure 25.3. A marking pen attached to the bob traces a sine curve on a sheet of paper that is moving horizontally at constant speed. Like a water wave, the high points on the wave are called crests. The low points on the wave are called troughs. The straight dashed line represents the home position or midpoint of the vibration. 25.3. A sine curve is a pictorial representation of a wave. The Sears Tower in Chicago sways back and forth at a frequency of about 0.1 hertz. What is its period of vibration? The period is 1 vibration over 0.1 hertz equals 1 vibration over 0.1 vibrations per second equals 10 seconds. The term amplitude refers to the distance from the midpoint to the crest or trough of the wave. So the amplitude equals the maximum displacement from equilibrium. The wavelength of a wave is the distance from the top of one crest to the top of the next one. Or equivalently, the wavelength is the distance between successive identical parts of the wave. The wavelengths of waves at the beach are measured in meters. The wavelengths of ripples in a pond in centimeters, and the wavelengths of light in billionths of a meter, nanometers. Frequency, the number of vibrations an object makes in a unit time, is an object's frequency. The frequency of a vibrating pendulum or object on a spring specifies the number of back and forth vibrations it makes in a given time, usually 1 second. A complete back and forth vibration is 1 cycle. If it occurs in 1 second, the frequency is 1 vibration per second, or 1 cycle per second. If 2 vibrations occur in 1 second, the frequency is 2 vibrations, or 2 cycles per second. The frequency of the vibrating source and the frequency of the wave it produces are the same. The unit of frequency is called the hertz. A frequency of 1 cycle per second is 1 hertz. 2 cycles per second is 2 hertz, and so on. Higher frequencies are measured in kilohertz, kHz, thousands of hertz, and still higher frequencies in megahertz, MHz, millions of hertz, or gigahertz, GHz, billions of hertz. AM radio waves are broadcast in kilohertz, while FM radio waves are broadcast in megahertz. Radar and microwave ovens operate at gigahertz. A station of 960 kilohertz broadcasts radio waves that have a frequency of 960,000 hertz. A station at 101 megahertz broadcasts radio waves with a frequency of 101 million hertz. As figure 25.4 shows, these radio wave frequencies are the frequencies at which electrons vibrate in the transmitting antenna of a radio station. If the frequency of a vibrating object is known, its period can be calculated, and vice versa. 25.4. Electrons in the transmitting antenna of a radio station at 960 kilohertz on the AM dial vibrate 960,000 times each second and produce a 960 kilohertz radio wave. Suppose, for example, that a pendulum makes 2 vibrations in 1 second. Its frequency is 2 hertz. The time needed to complete 1 vibration, that is, the period of vibration, is 1/2 second. Or, if the vibration period is 3 hertz, then the period is 1/3 second. As you can see below, frequency and period are inverses of each other. Frequency equals 1 over period, or period equals 1 over frequency. Concept check. What is the source of all waves? 25.3. Wave motion. Most of the information around us gets to us in some form of wave. Sound is energy that travels to our ears in the form of a wave. Light is energy that comes to our eyes in the form of a different kind of wave, an electromagnetic wave. The signals that reach our radio and television sets also travel in the form of electromagnetic waves. When energy is transferred by a wave from a vibrating source to a distant receiver, there is no transfer of matter between the 2 points. To see this, think about the very simple wave produced when one end of a horizontally stretched spring is shaken up and down, as shown in figure 25.5. 25.5. When the string is shaken up and down, a disturbance moves along the string. Noisy bugs linked to entomology. Big bumblebees flap their wings about 130 flaps per second and produce sound of 130 hertz. A honeybee flaps its wings at 225 flaps per second and produces a higher pitched sound of 225 hertz. The annoying high-pitched whine of a mosquito results from its wings flapping at 600 hertz. These sounds are produced by pressure variations in the air caused by vibrating wings. After the end of the string is shaken, a rhythmic disturbance travels along the string. Each part of the string moves up and down while the disturbance moves horizontally along the length of the string. It is the disturbance that moves along the length of the string, not parts of the string itself. Drop a stone in a quiet pond and you'll produce a wave that moves out from the center in an expanding circle, as shown in figure 25.6. It is the disturbance that moves, not the water. For after the disturbance passes, the water is where it was before the wave passed. When someone speaks to you from across the room, the sound wave is a disturbance in the air that travels across the room. The air molecules themselves do not move along as they would in the wind. 25.6. A circular water wave in a still pond moves out from the center in an expanding circle. The air, like the rope and the water in the previous examples, is the medium through which the wave energy travels. Energy is not transferred by matter moving from one place to another within the medium. The energy transferred by a wave from a vibrating source to a receiver is carried by a disturbance in a medium. Concept check. How does a wave transfer energy? Discover making waves, part 1. Oscillate a marking pen back and forth across a piece of paper as you slowly pull the paper in a direction perpendicular to your oscillation. Repeat step 1, but pull the paper faster this time. 3. Think. What happens to the wavelength of the curves when you pull the paper faster? Part 2. Repeatedly dip your finger into a wide pan of water to make circular waves on the surface. Repeat step 1, but dip your finger more frequently. 3. Think. What happens to the wavelength of the waves when you dip your finger more frequently? 25.4. Wave speed. The speed of waves depends on the medium through which the wave moves. Sound waves, for example, move at a speed of 330 meters per second to 350 meters per second in air, depending on temperature, and about 4 times faster in water. Whatever the medium, the speed, wavelength, and frequency of the wave are related. Consider the simple case of water waves as shown in figure 25.7. Notes: the equation V equals lambda F makes sense. During each vibration, a wave travels a distance of one wavelength. Figure 25.7. If the wavelength is 1 meter and 1 wavelength per second passes the pole, then the speed of the wave is 1 meter per second. Think. If a water wave vibrates up and down 2 times each second, and the distance between wave crests is 1.5 meters, what is the frequency of the wave? What is its wavelength? What is its speed? The frequency of the wave is 2 hertz. Its wavelength is 1.5 meters, and its wave speed is lambda times f, which equals 1.5 meters times 2 hertz equals 3 meters per second. Imagine that you fix your eyes on a stationary point on the surface of water and observe the waves passing by this point. If you observe the distance between crests, the wavelengths, and also count the number of crests that pass each second, the frequency, then you can calculate the horizontal distance a particular crest moves each second. For example, in figure 25.7, 1 crest passes by the bird every second. The waves therefore move at 1 meter per second. You can calculate the speed of a wave by multiplying the waves by the frequency. For example, if the wavelength is 3 meters, and if 2 crests pass a stationary point each second, then 3 meters times 2 waves pass by in 1 second. The waves therefore move at 6 meters per second. In equation form, this relationship is written as V equals lambda F, where V is the wave speed, lambda, Greek letter lambda, is wavelength, and F is wave frequency. This relationship holds for all kinds of waves, whether they are water waves, sound waves, radio waves, or light waves. Table 25.1 shows some wavelengths and corresponding frequencies of sound in air at the same temperature. Think, what is the wavelength of a 340 hertz sound wave when the speed of sound in air is 340 meters per second? The wavelength must be 1 meter. Then wave speed equals 1 meter times 340 hertz equals 340 meters per second. Notice that the product of wavelength and frequency is the same for each example, 340 meters per second in this case. During a concert, you do not hear the high notes in a chord before you hear the low notes. The sounds of all instruments reach you at the same time. Notice that long wavelengths have low frequencies and short wavelengths have high frequencies. Wavelength and frequency vary inversely to produce the same wave speed for all sounds. Concept check. How do you calculate the speed of a wave? Do the math. If a train of freight cars, each 10 meters long, rolls by you at a rate of 2 cars each second, what is the speed of the train? You can look at this problem in two ways, the Chapter 4 way and the Chapter 25 way. For Chapter 4, we recall that V equals d over t, which equals 2 times 10 meters divided by 1 second equals 20 meters per second. Note that d is the length of that part of the train that passes you in time t. Here in Chapter 25, we compare the train to wave motion, where the wavelength corresponds to 10 meters and the frequency is 2 hertz. Then wave speed equals wavelength times frequency, where V equals 10 meters times 2 hertz equals 20 meters per second. One of the nice things about physics is that different ways of looking at things produce the same answer. When this doesn't happen and there is no error in computation, then the validity of one or both of those ways is suspect. 25.5 Transverse waves. Suppose you create a wave along a rope by shaking the free end up and down as shown in figure 25.8. The motion of the rope is at right angles to the direction in which the wave is moving. Whenever the motion of the medium is at right angles to the direction in which a wave travels, the wave is a transverse wave. Waves in the stretched strings of musical instruments and the electromagnetic waves that make up radio waves and light are transverse. Concept check. What are some examples of transverse waves? Figure 25.8. A person creates a transverse wave by shaking the free hand of rope up and down. The arrows represent the motion of the rope. 25.4 Longitudinal waves. Not all waves are transverse. Sometimes the particles of the medium move back and forth in the same direction in which the wave travels. When the particles oscillate parallel to or along the direction of the wave rather than at right angles to it, the wave is a longitudinal wave. Sound waves are longitudinal waves. Both transverse and longitudinal waves can be demonstrated with a loosely coiled spring as shown in figure 25.9. A transverse wave is demonstrated by shaking the end of a coiled spring up and down. Figure 25.9. Transverse and longitudinal waves transfer energy from left to right. A. When the end of the coiled spring is shaken up and down, a transverse wave is produced. B. When it is shaken in and out, a longitudinal wave is produced. A longitudinal wave is demonstrated by shaking the end of a coiled spring in and out. In this case, we see that the medium vibrates parallel to the direction of energy transfer. Concept check. What is an example of a longitudinal wave? Seismologist, physics on the job. When an earthquake occurs, the sudden release of energy produces waves. Seismologists study and interpret those waves in order to determine the strength and location of the earthquake. They compare the speed, amplitude, and reception of primary longitudinal waves with secondary transverse waves. Because they understand how waves travel and the materials through which they pass, seismologists are able to describe earthquakes, learn about the composition of Earth, and possibly predict future earthquakes. Seismologists conduct research from university and government facilities such as the National Earthquake Information Service, NEIS, in Colorado. 25.7. Interference. A material object such as a rock will not share its space with another rock, but more than one vibration or wave can exist at the same time in the same space. If you drop two rocks in water, the waves produced by each can overlap and form an interference pattern. An interference pattern is a regular arrangement of places where wave effects are increased, decreased, or neutralized. Interference patterns occur when waves from different sources arrive at the same point, at the same time. In constructive interference, the crest of one wave overlaps the crest of another, and their individual effects add together. The result is a wave of increased amplitude, as figure 2510a shows. This is called reinforcement. In destructive interference, the crest of one wave overlaps the trough of another, and their individual effects are reduced. The high part of one wave simply fills in the low part of another, as figure 2510b shows. This is called cancellation. Wave interference is easiest to see in water. Figure 2511a shows the interference pattern made when two vibrating objects touch the surface of water. The gray spokes are regions where waves cancel each other out. 2510. There are two types of wave interference. A. In constructive interference, the waves reinforce each other to produce a wave of increased amplitude. B. In destructive interference, the waves cancel each other and no wave is produced. 2511. A. Two overlapping water waves produce an interference pattern. B. Overlapping concentric circles produce a pictorial representation of an interference pattern. At points along these regions, the waves from the two objects arrive out of step or out of phase with one another. When waves are out of phase, the crest of one wave overlaps the trough of another to produce regions of zero amplitude. The dark and light striped regions are where the waves are in step or in phase with each other. When waves are in phase, the crest of one wave overlaps the crest of another, and the troughs overlap as well. Notes: sound, a longitudinal wave, requires a medium. It can't travel in a vacuum because there's nothing to compress or stretch. Interference patterns are nicely illustrated by the overlapping of concentric circles printed on pairs of clear sheets, as in figure 2511b and 2512. When the sheets overlap with their centers slightly apart, a so-called moire pattern is formed that is very similar to the interference pattern of water waves or any kind of waves. A slight shift in either of the sheets produces a noticeable difference pattern. If a pair of such sheets is available, be sure to try this and see the variety of patterns for yourself. Figure 2512, a moire pattern is very similar to an interference pattern. Interference is characteristic of all wave motion, whether the waves are water waves, sound waves, or light waves. The interference of sound is discussed in the next chapter, and the interference of light in chapter 31. Concept check: what causes interference patterns? 25.8. Standing waves. If you tie a rope to a wall and shake the free end up and down, you will produce a wave in the rope. The wall is too rigid to shake, so the wave is reflected back along the rope to you. By shaking the rope just right, you can cause the incident, original, and reflected waves to form a standing wave. A standing wave is a wave that appears to stay in one place. It does not seem to move through the medium. Certain parts of the standing wave remain stationary. Nodes are the stationary point in the standing wave. Interestingly enough, you could hold your finger on either side of the rope at the node and the rope would not touch them. Other parts of the rope would make contact with your fingers. Think, is it possible for one wave to cancel another wave so that the combined amplitude is zero? Explain your answer. Yes, this is called destructive interference. In a standing wave, for example, parts of the wave have no amplitude, the nodes. The positions on a standing wave with the largest amplitudes are known as antinodes. Antinodes occur halfway up between the nodes. Standing waves are the result of interference. When two waves of equal amplitude and wavelength pass through each other in opposite directions, the waves are always out of phase at the nodes. In figure 2513 shows the nodes are stable regions of destructive interference. You can produce a variety of standing waves by shaking the rope at different frequencies. Once you find the frequency that produces a standing wave, doubling it or tripling the frequency will also produce a standing wave. 2513. The incident and reflected waves interfere to produce a standing wave. The nodes are places that remain stationary. A standing wave forms only in half a wavelength, or a multiple of half a wavelength fits exactly into the length of the vibrating medium. In figures 2514a, the rope length equals half a wavelength. In figure 2514b, the rope length equals one wavelength. In 2514c, the rope length equals 1.5 wavelengths. If you keep increasing the frequency, you'll produce more interesting waves. Standing waves are set up in the strings of musical instruments that are struck. 2514. You can produce a variety of standing waves. A. Shake the rope until you set up a standing wave of 1/2 wavelength. B. Shake with twice the frequency and produce a standing wave of 1 wavelength. Shake with 3 times the frequency and produce a standing wave of 1.5 wavelengths. They are set up in the air in an organ pipe and the air of a soda pop bottle when air is blown over the top. Standing waves can be produced in either transverse or longitudinal waves. Concept check. At what wavelengths can a standing wave form in a vibrating medium? 25.9. The Doppler Effect. Imagine a bug jiggling its legs and bobbing up and down in the middle of a quiet puddle, as shown in figure 2515. Suppose the bug is not going anywhere, but is merely treading water in a fixed position. The crest of the wave it makes are concentric circles because the wave speed is the same in all directions. If the bug bobs in the water at a constant frequency, the distance between wave crests, the wavelength, will be the same for all successive waves. waves encountered point A as frequently as they encounter point B. This means that the frequency of wave motion is the same at point A and B, or anywhere in the vicinity of the bug. 2515, a stationary bug jiggles in still water, produces a circular water wave. This will become more important as the chapter unfolds. Think, when a source moves towards you, do you measure an increase or decrease in wave speed? Neither. It is the frequency of the wave that undergoes a change, not the wave speed. Police officer, physics on the job. Police officers are responsible for protecting people. While that involves catching criminals and solving crimes, it also requires that police officers prevent drivers from speeding. In this way, police officers protect pedestrians and people in vehicles. One way the police officer prevents speeding is by using radar equipment. Radar equipment sends waves towards the moving vehicle and uses the Doppler effect to determine the speed of the vehicle. By knowing how to operate the device, police officers can determine when a driver is not obeying the speed limit. Let's study this picture carefully. This wave frequency is the same as the bobbing frequency of the bug. Suppose the jingling bug moves across the water at a speed less than the wave speed. In effect, the bug chases part of the crest it has produced. The wave pattern is distorted and is no longer concentric, as shown in figure 2516. The center of the outer crest was made when the bug was at the center of that circle. The center of the next smaller crest was made when the bug was at the center of that circle, and so forth. The centers of the circular crest move in the direction of the swimming bug. Although the bug maintains the same bobbing frequency as before, an observer at B would encounter the crest more often. The observer would encounter a higher frequency. 2516, a bug swimming in still water produces a wave pattern that is no longer concentric. This is because each successive crest has a shorter distance to travel, so they arrive at B more frequently than if the bug were not moving towards B. An observer at A, on the other hand, encounters a lower frequency because of the longer time between wave crest arrivals. To reach A, each crest has to travel farther than the one ahead of it due to the bug's motion. As a wave source approaches, an observer encounters waves with a higher frequency. As a wave approaches, an observer encounters waves with a higher frequency. As a wave source moves away, an observer encounters waves with a lower frequency. Notes: bats hunt moths in darkness by echolocation and the Doppler effect. Some moths are protected by a thick covering of fuzzy scales that deaden the echoes. This apparent change in frequency due to the motion of the source or receiver is called the Doppler effect, after the Australian scientist Christian Doppler, 1803 to 1853. The greater the speed of the source, the greater will be the Doppler effect. Water waves spread over the flat surface of the water. Sound and light waves, on the other hand, travel in three-dimensional space in all directions like an expanding balloon. Just as circular wave crests are closer together in front of the swimming bug, spherical sound or light wave crests ahead of a moving source are closer together than those behind the source and encounter a receiver more frequently. Sound. The Doppler effect is evident when you hear the changing pitch of a siren as a fire truck passes you. Look at figure 2517. When the fire truck approaches, the pitch sounds higher than normal. This occurs because the sound wave crests are encountering you more frequently. Figure 2517. The pitch of sound is higher when the source moves towards you and lower when the source moves away. Police make use of the Doppler effect of radar waves in measuring the speeds of cars on the highway. Radar waves are electromagnetic waves, lower in frequency than light and higher in frequency than radio waves. Police bounce them off moving cars, as shown in figure 2518. A computer built into the radar system calculates the speed of the car relative to the radar unit by comparing the frequency of the radar with the frequency of the reflected waves, light. The Doppler effect also occurs for light. When a light source approaches, there is an increase in the measured frequency, and when it recedes, there is a decrease in its frequency. Figure 2518, the police calculate a car's speed by measuring the Doppler effect of radar waves. An increase in frequency is called a blue shift because the increase is towards the high frequency or blue end of the color spectrum. A decrease in frequency is called a red shift, referring to the low frequency or red end of the color spectrum. Distant galaxies, for example, show a red shift in the light they emit. A measurement of this shift enables astronomers to calculate their speeds of recession. A rapidly spinning star shows a red shift on the side turning away from us and a blue shift on the side turning toward us. This enables a calculation of the star's spin rate. Concept check. How does the apparent frequency of waves change as a wave source moves? 2510. Bow waves. When the speed of the source in a medium is as great as the speed of the waves it produces, something interesting happens. The waves pile up. Consider the bug in the previous example when it swims as fast as the wave speed. Can you see that the bug will keep up with the wave crest it produces? Instead of the crests getting ahead of the bug, they pile up or superimpose on one another directly in front of the bug, as suggested in figure 2519. The bug moves right along with the leading edge of the waves it is producing. The same thing happens when an aircraft travels at the speed of sound. 2519, a bug swimming at the wave speed keeps up with the wave crests it produces. In the early days of jet aircraft, it was believed that this pileup of sound waves in front of the airplane imposed a sound barrier, and that to go faster than the speed of sound, the plane would have to break the sound barrier. What actually happens is that the overlapping wave crests disrupt the flow of air over the wings, so that it is harder to control the plane when it is flying close to the speed of sound. But the barrier is not real, just as a boat can easily travel faster than the speed of the water waves. An airplane with sufficient power can easily travel faster than the speed of sound. Then we say that it is supersonic, faster than sound. A supersonic airplane flies into smooth, undisturbed air because no sound wave can propagate out in front of it. Similarly, a bug swimming faster than the speed of water waves finds itself always entering into water with a smooth, unrippled surface. When the bug swims faster than wave speed, ideally it produces a wave pattern as shown in figure 2520. It outruns the wave crests it produces. The crests overlap at the edges, and the patterns made by these overlapping crests is a V-shaped, called a bow wave, which appears to be dragging behind the bug. A bow wave occurs when a wave source moves faster than the waves it produces. The familiar bow wave generated by a speedboat knifing through the water is produced by the overlapping of many circular wave crests. 2520. A bug swimming faster than the wave speed produces a wave pattern in which the wave crests overlap the edges. Figure 2521 shows some wave patterns made by sources moving at various speeds. After the speed of the source exceeds the wave speed, increased speed produces a bow wave with a narrower V shape. Concept check. What causes a bow wave? 2521. The wave patterns made by a swimming bug at successively greater speeds change. Overlapping at the edges occurs only when the source travels faster than wave speed. 2511. Shock waves. A speedboat knifing through the water generates a two-dimensional bow wave. A supersonic aircraft similarly generates a shock wave. A shock wave is a three-dimensional wave that consists of overlapping spheres to form a cone. A shock wave occurs when an object moves faster than the speed of sound. Just as the bow wave of a speedboat spreads until it reaches the shore of the lake, the conical shock wave generated by a supersonic craft spreads until it reaches the ground, as shown in figure 2522. The bow wave of a speedboat that passes by can splash and douse you if you are at the water's edge. 2522. A shock wave is swept continuously behind a supersonic aircraft. In a sense, you can say that you are hit by a water boom. In the same way, a conical shell of compressed air sweeps behind a supersonic aircraft. The sharp crack heard when the shock wave that sweeps behind a supersonic aircraft reaches the listener is called a sonic boom. We don't hear a sonic boom from a slower than sound or subsonic aircraft because the sound wave crests reach our ears one at a time and are perceived as a continuous tone. Only when the aircraft moves faster than sound do the crests overlap and encounter the listener in a single burst. The sudden increase in pressure has much the same effect as the sudden expansion of air produced by an explosion. Both processes direct a burst of high pressure air to the listener. The ear cannot distinguish between the high pressure from an explosion and the high pressure from many overlapping wave crests. A common misconception is that sonic booms are produced at the moment that an aircraft flies through the sound barrier. That is, just as the aircraft surpasses the speed of sound. This is equivalent to saying that a boat produces a bow wave only when it first overtakes its own waves. This is not so. The fact is that a shock wave and its resulting sonic boom are swept continuously behind an aircraft traveling faster than sound, just as a bow wave is swept continuously behind a speedboat. In figure 2523, Listener B is in the process of hearing a sonic boom. Listener A has already heard it, and listener C will hear it shortly. Figure 2523. The shock wave has not yet encountered listener C, but is now encountering listener B, and has already passed listener A. Notes: don't confuse supersonic with ultrasonic. Supersonic has to do with speed, faster than sound. Ultrasonic involves frequency, higher than we can hear. The aircraft that generated the shock wave may have broken through the sound barrier hours ago. It is not necessary that a moving source emits sound for it to produce a shock wave. Once an object is moving faster than the speed of sound, it will make sound. A supersonic bullet passing overhead produces a crack, which is a small sonic boom. If the bullet were larger and disturbed more air in its path, the crack would be more boom-like. When a lion tamer cracks a circus whip, the cracking sound is actually a sonic boom produced by the tip of the whip when it travels faster than the speed of sound. Snap a towel, and the end can exceed the speed of sound and produce a mini sonic boom. The bullet, whip, and towel are not in themselves sound sources, but when traveling at supersonic speeds, they produce their own sound as waves of air are generated to the sides of the moving object. On the matter of sound in general, you know that you'll damage your eyes if you stare at the sun. What many people don't know is that you'll similarly damage your ears if you overexpose them to loud sounds. Do as your author does when in a room with very loud music. Leave. If for any reason you don't want to leave, really enjoyable music or good camaraderie with friends, stay, but use earplugs of some kind. When you're not being a wimp, when you give the same care to your ears that you give to your eyes. Concept check. What causes a shock wave? Notes. Watch for the advent of the newly designed aircraft that flies 1.8 times the speed of sound and produces sonic booms only 1/100th the strength of the supersonic Concorde, which was grounded following a fatal accident in 2000. Summary: vibrations and waves. The period of a pendulum depends only on the length of the pendulum and the acceleration of gravity. The source of all waves is a vibration. The energy in waves is carried by a disturbance in a medium. Calculate the wave by multiplying the wavelength and the frequency. Waves in the stretched springs of musical instruments and electromagnetic waves are transverse. Sound waves are longitudinal. Interference patterns occur when waves from different sources arrive at the same point, at the same time. A standing wave forms if a multiple of half a wavelength fits into the length of the medium. As a wave source approaches, an observer encounters waves with a higher frequency. As a wave source moves away, an observer encounters waves with a lower frequency. A bow wave occurs when a wave source moves faster than the wave it produces. A shock wave occurs when an object moves faster than the speed of sound.